All right, so let's look at this exam. What do we get? New term. Oh, guess I don't have to go through it this way. I can do it. I can do it like this. All right, so first one, write an error-free hello world program. You could have included, all the namespace stuff and things like that, but I was mainly looking for the kind of the main part of it. But let's go ahead and do this here real quick. All right, so error-free hello world program. Oh, that's gonna need to hide that. All right, so we have a number include iostream.h. You could have done the using namespace std if you wanted. I didn't care if you had that in there or not. Then something like int main. And I know this was capitalizing crap, but I'll fix that in a second. And then something like cout hello world. If you just left it like that, that's fine. It won't kick it down the line, but not the end of the world. Similarly, you could have done like a return 0. I don't care if you had that or not. So basically something along these lines showing me that you understand that all programs begin and end with main, and you're able to get a functional program right from the get-go to start any project. Make some sense? All right, something along those lines, or at least close enough. All right, next question. Write 3 small code-based examples showing how C++ has mechanisms for the 3 ways humans solve problems: memory, asking questions, and repetition. All right, so let's look at this. So for memory, oh, that's not how you spell memory. For memory, we might say something like int a is equal to 5. All right, code example for memory. Create variable. All right, for asking questions, you might have if a is less than 10, cout woot or something like that. All right, so there's a code example of asking a question. If you made it more complex than that, it's fine. You put an else in there, whatever, but that's a code for asking a question. Last one was repetition, right? Yeah, repetition. So repetition would probably be a loop, right? So you could do something like a for loop for int I is equal to 0, I is less than 10, I plus plus, cout I, whatever, something along those lines. So show me some code that shows you how to write a loop, how to write an if statement, and how to define a variable, and connect them with your understanding that all programming languages have facilities for the way human beings solve problems: memory, asking questions, repetition. Make sense? All right, so something along these lines. It didn't matter if you did it more involved than this, but this was simple enough. Show me you understand that connection with those structures. Questions about that one? Okie. Convert. All right, let me paste this in here. Do I want to? Maybe I want a new slide for this. All right, convert ABC123 from hexadecimal to binary. Okay, I specifically picked hexadecimal to binary because that supports the shortcut dealy flippy thingy. All right, So remember you did that paper on why do we have these different bases, hexadecimal, octal, decimal, binary. And one of the reasons we use hexadecimal, not only to have shorter footprints, smaller footprints for our memory addresses, but it's also very convenient to move between. So you're good? You emailed me? All right, perfect. So it's very easy to move between hexadecimal and binary. All right, so we'll go ahead and do this one. Now, nothing actually prevents you from first converting this to decimal and then converting it to binary if you're a glutton for punishment, right? It will work. It will give you the correct answer. All right, but I'm sure several of you did that, right? All right, so which is okay, but I'm pretty sure I said that I'll probably put something with the shortcuts on the exam. All right, so what we do is, remember, for hexadecimal, we can represent all of the hextets with 4 bits. So 0 through 9, A through F. 0 is 0, 0, 0, 0. F is 1, 1, 1, 1. So we have all the hextets. So for A, we're effectively going to say, what's the binary value? 11 or 10, then 11, then 12, then 1, then 2, then 3. All right. So binary value for, let's actually go right to left because that's the way this will fill in. So a 3 is 0, 0, 1, 1. So this is a 1 in the ones place, a 1 in the twos place. So that's a 3. A 2 is a 0, 0, 1, 0. A 1 is a 0, 0, 0, 1. A 12, so we have the ones place, the twos place, the fours place, the eights place. So we need to have an 8 and a 4. So this is 1, 1, 0, 0. An 11 is going to be 1, 0, 1, 1. So that's a 1 in the eights place, a 1 in the twos place, and a 1 in the ones place. And then a 10 is 1, 0, 1, 0. A 1 in the twos place and a 1 in the eights place. So there is the binary version of that number. All right. So hexadecimal, you just rewrite every one of the hextets in a 4-bit binary number. Okay. Otherwise, if you went, man, that's gonna suck. So we can, man, you people. All right, so if we want to old school this, and I did say you can use a calculator. So this 3 is in the ones place. The 2 is in the 16s place. Let me spread these guys out a little bit just to make it a little cleaner. This 1 is in the 256 place. $40.96 place is the C. Oh man, well, whatever. 65,536. 65,536. And 1 million. Can I just copy that? Nailed it. All right. So let's. All right. We're just going to say that's close enough. All right. So now we have to do the math. Remember that this A is actually a 10. The B is actually an 11. The C is actually a 12, right? So the math for this is 10 times that guy. Oh, come on, you can do it. Plus 11 times 65,536 plus 12 times 4096 plus 1 times 256 plus 2 times 16 plus 3 times 1. I get that right? 10 times that number, 11 times that number, 12 times that number, 1 times that number, 2 times that number, and 3 times that number. Okay. So put all that in and we get 11,256,099. Is that the number? 11,256,099. Okay. So that is the decimal equivalent of that number. All right, now we convert that guy into crap binary by dividing by 2 5 zillion times, recording the remainders. Hey. How many of you wish you used the shortcut? All right, well, I'm gonna need probably multiple slides here. Let's just, where am I going? Let's do this. See if I can get away with it with maybe two columns. This might be a 3-column situation. Okie dokie. What's my starting number? This guy. So we have that number divided by 2. So that number divided by 2 is this guy with a remainder of 1. All right, because this guy times 2 is 1 short of this guy. All right, so then this number divided by 2 is this guy with a remainder of 1, because this guy times 2 has something left over to get to this guy. This guy divided by 2 is this guy with a remainder of 0. There's nothing left over. This guy divided by 2 is this guy, remainder 0. This guy divided by 2, is that guy, remainder 0. That guy divided by 2 is that guy, remainder 1. That guy divided by 2 is this guy, remainder 0. That guy divided by 2 is that guy remainder 0. That guy divided by 2 is this guy remainder 1. That guy divided by 2 is this guy remainder 0. Okay, let's bounce up to the the next let's go over to the next column. So that guy divided by 2 is this guy remainder 0. That guy, oops, ninja. That guy divided by 2 is this guy remainder 0. That guy divided by 2 is that guy remainder 0. That guy remainder 2 is that guy remainder 0. That guy, oops, that guy remainder 2 is that guy remainder 1, or divided by 2 rather, is that guy remainder 1. That guy divided by 2 is this guy remainder 1. 172 divided by 2. Oh, it's 171, right? Is this guy remainder 1? I think I should stick with the copying and pasting. That guy divided by 2 is this guy remainder 1. That guy remainder 2, or divided by 2, is this guy. That guy divided by 2 is 10, remainder 1. 10 divided by 2 is 5, remainder 0. 5 divided by 2 is 2, remainder 1. 2 times 2 is 4, with 1 left over to get to 5. 2 divided by 2 is 1 with a remainder of 0. 1 divided by 2 is 0 with a remainder of 1. And we know we're done when we hit that 0. We read our answer from bottom up. One zero one zero one zero one 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 zero 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 100100011. I think I typed that right. And if you want, you can break it into your groupings of 4s. I think that should match. Ta-da! I gotta go take a break. All right. So use the shortcut. But remember, the shortcut only works for octal, hexadecimal, base 16, and it will also work for base 32. Which means that for all the 32, whatever the names of the digits are for base 32, not hextets, not octets, not digits, not bits, but whatever its name is, it could be fully represented in 5 bits, right? All right, questions about that one? The intention was for you to do it this way. This way is better. But at least we proved you could do it the other way. All right. Next one, convert this value from decimal to hexadecimal. All right, so this is having to prove that you know how to do the other pattern. All right, so I'm gonna steal this guy. Just in case I need to. All right, so we have 62,091. We're going to divide that guy by 16 because we're going from decimal to hexadecimal. So that guy divided by 16 is this dude. This dude times 16 gives me 62,080. So that's a remainder of an 11. This guy divided by 16 gives me 242.5. 242 times 16 is 3872. So that's a remainder of 8. $242 divided by 16 is 15. 15 times 16 is 240. So that's a remainder of 2. $15 divided by 16 is 0. Right? 16 goes into 15 0 times. 0 times 16 is 0. So we have a remainder of 15. All right, we need to remember to replace our double digits. So this is actually a B. This is actually an F. And then we read our answer from bottom up. So this is F28B. All right, questions about that one? And that's the identical pattern to what we did here. It just was a lot fewer things because we were divided by 16 rather than dividing by 2. Okay. Write the lines of code needed to display the numbers 15,000 down to 1,000 to the screen, one line at a time. All right, you could have decided whether to include 1,000 or not include 1,000 in it, but the larger structure of your for loop should be the same. So we're going to have a for loop, weren't I? And if you wanted to write this in a different kind of loop, you could. We're going to start it at 15,000. We're going to keep going as long as I is greater than, I'll just assume that we're going to include 1,000 in this. So I'll say greater than or equal to 1,000. And each time through, we're going to say I is equal to I minus 1. I'll fix the capitalization in a minute. And we're going to display these to the screen. So this is a cout current value of I. If you want to kick it down the line, you can, not required. So for loop starts at 15,000, keeps going as long as it's greater than or equal to 1,000. Each time through, I gets 1 subtracted from it. Print out I each time through. So that will display the numbers 15,000 down to 1,000 to the screen 1 line at a time. I guess technically the /n needed to be there for the 1 line at a time part, but I probably wouldn't take points off if that's the one thing you were missing. All right, questions about that one? Next one. Write a function named midterm that takes 3 integers as parameters and returns the smallest of the 3 integers. All right, so in this case, we're writing a function. And specifically, it's going to return a value. All right, so this guy's returning an int. I'll fix the capitalization again at the end. It's going to be called midterm. It's taking 3 integers as parameters. So int A, int B, int C, for example. Oh, I'll fix that at the end, I guess. All right, so we want to return the, what am I returning? The smallest of the 3 numbers. So let's find out who's smaller between A and B. So if A is less than B, then we want to find out if A is also less than C, right? But we could actually write a couple of values here. So we can start off with, we could say int smaller, and we could say if A is less than B, we can say smaller is equal to A. Else smaller is equal to B. So after that if statement, my variable name smaller holds the smaller value of A and B, right? Start off with variable smaller called smaller, ask the question, if A is smaller than B, then store A inside of smaller, otherwise store B inside of smaller. So after that if statement, we have stored inside of a variable named smaller the smaller value between A and B. So now we have to ask the question of smaller versus C. If smaller is less than C, if I want, I can keep going with the variable smaller and return at the end, or I can just say I'm going to return smaller right here. The smaller I know holds the value that is the smaller value between A and B. And I just compared it to C, and if smaller is smaller than C, I can just return smaller. Otherwise, C must be the smallest value. So I'll return C. Let's clean this up. It really wants to capitalize everything here, doesn't it? All right, so something along those lines. There's several different kind of approaches you could have taken with this to whittle it down, but ultimately this will return the number that is the smallest number out of those 3 numbers. All right, questions about that one? All right. Write a function named do something that takes an integer as a parameter and displays to the screen all of the numbers between 1 and that integer that are evenly divisible by 5. All right, so we are displaying something to the screen. We are not returning a value, right? So my return type will be void. And we're going to call this guy do something. It's going to take in a single integer as a parameter. And we want to display all the numbers between between 1 and that integer that are evenly divisible by 5. So we want to have a loop that's going to take I on a voyage between 1 and whatever value I passed in. And you can decide whether it's equal to that value or one less than that value. So we'll say int I is equal to 1. We're starting off at 1, not 0. I is less than or equal to A. I is equal to I plus 1. Each time through, we're going to ask a question if the current value of I, when divided by 5, has a remainder of 0. See out the current value of I. All right. So function name do something. That's going to be displaying some stuff, not returning a value. That's why its return type is void. We're going to take a single integer as a parameter. I'm going to write a loop that takes I on a voyage between 1 all the way up to that integer. My example here includes that integer. If you chose to interpret my question as not including that integer, that's fine. Your logic will be the same. So all the way up to and including A, incrementing I by 1 each time. So this will go from 1 to 2 to 3 to 4 to 5. But inside there, I ask a question. If the current value of I, when I divide it by 5, has a remainder of 0, which means it's evenly divisible by 5, I'll go ahead and print it out. So I'm only printing out the values of I that are evenly divisible by 5. If I don't trip this, I won't print anything out. It'll just loop back up to the next I. All right, questions about that one? What is the difference between single equal sign and double equal sign in C++? Oh, Ninja. No. Equal sign is the assignment operator used when we are defining a variable or updating the value of a variable. Double equal sign is the equivalence operator that we use to create Boolean expressions used in if statements and loops. Something along those lines? Questions about that? Okay. What is variable scope in computer programming? All right, variable scope in computer programming. This is where in the program a variable is accessible. You could have gone into more detail and talked about how rule of thumb might be that's every opening and closing curly brace has a scope. That's not 100% true, but it's pretty close to always true. But really, when we talk about scope, we're talking about if I define a variable, where else in my program can I access that variable? Make sense? So you could have got more wordy than this, and that's fine. So as long as you convinced me that you understand the concept of variable scope, you'll be fine. So lots of ways you can convince me you understood the concept of variable scope. What is a Boolean expression? When is it used in a computer program? A Boolean expression is any expression that boils down to a single value of true or false. You could have also just said true or false. But I like to really emphasize the idea of it boiling down to true or false, because sometimes you're going to see Boolean expressions that are much, much, much more complex looking. It'll be, is this less than this? And if this is more than this, and did the user press a key? And yada, 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 all these things. And all of that ultimately will boil down to a single value of true or false. When at a glance, it maybe looked scarier than that. But something along these lines. When is it used in computer programming? It is used in if statements and loops. Primarily, nothing keeps you from, defining a Boolean, I guess in C++, it's bool b is equal to 5 less than 7. Nothing actually keeps you from defining a variable of type Boolean and storing in it the result of a Boolean expression. But generally speaking, the places we would run into Boolean expressions will be when we're creating if statements and when we're creating loops. Questions about that one? All right. Is that it? All right. So that is it. All right. So hopefully, understanding going into the exam, I mentioned that for most of you beginning programmers, the programming questions are the harder ones, right? But hopefully when you see it up here, it made sense when you saw the answer. That always happens first. Okay, and you're looking at that's it. That's all he wanted was that. That is perfectly normal. So if that is your current condition, that when you see it, it makes sense to you, you're in an okay place. It just hasn't clicked yet. Okay. So don't freak out about that. That's the way it happens for everyone. Let's see. So the Hello World program, that one should have been a toss-up. I told everybody it was going to be on there, right? So that should have been free points. Examples of variables, if statements, repetition should not have been too big of a deal. I wasn't really asking you to problem solve anything in real time. I was mainly asking you to give me an example of how C++ does that. So really you should have been able to do that one, I think, for most of you. The conversion question, I could see how this question here might have ticked you off if you didn't remember to use the shortcut. Certainly frustrated me. But certainly this is something you should have been able to do, right? We did it in class. We've written some programs that accomplish this. On exams, I told you that basically anytime you ever have a Lippmann exam during your 4 years of school here, there will be a conversion question on every exam, even though it has nothing to do with that class. And I know it might seem stupid, but I promise you, understanding how things work under the hood will allow you to solve problems that other people won't be able to solve. You won't think in that mindset about the different bases, or the different ways we represent things, if this isn't second nature to you. So what I did see from some people is I didn't ask you to write any code. I didn't ask you to write a function that did this, but instead you wrote some program that tried to solve this problem, whether it was close or not close, rather than just doing the math, right? So this is just a math problem. All right. So should have been a layup, perhaps with a small math mistake or something like that, right? I mean, especially with this one, if you had to go the route of doing it longhand, Yeah, so I mean, obviously you would have been error prone with that many divisions by 1 and by 2 and stuff like that. So of course that's a 0. It's a no points for that one. Hopefully you showed me work, and if you showed me your work, I'll see where you made your mistake, and you'll probably get a 9 out of 10, or if it's a funny mistake, I might even just give you a 10 out of 10. I always find that funny when students do all the work right and they have the correct answer, and then when they go to write it down below to put like a little square around it or something, not that they have to, they like leave like the last number off, something like that. Then I give them no points as well and just wait for them to freak out. All right, so as long as you showed your work, which I told you to do, show your work, I will hopefully find where your math mistake was and you won't get killed for a small little mistake. This one should have been pretty straightforward, easier. Similarly, though, if you show me your work, and you made a little math mistake, it'll be fine. Mainly what I'm looking for in this one, besides the correct answer, let's say, is that you knew to map between the numbers and the letters for things above 10 and above. And then also that you use the right pattern from going from decimal to hexadecimal. You didn't put this number there and say, okay, well, this is the 1's place, the 16's place, the 32's place, right? Using the wrong pattern for doing the conversion. So did you know which pattern to use? And did you know to convert things that were double digits to letters? All right. And then was your math reasonably sound? This one, I think most of you should have been able to do, or at least take a pretty safe stab at it. So, this is, we're just writing a single loop. We've done that for a while now. I can see a little bit, maybe you're still struggling with some of the syntax up here or whatever, but this isn't doing a whole lot of heavy logic and stuff. So I think this one should have been in most people's wheelhouse. So if you felt inclined to leave this one blank, you didn't know where to start, it's probably worth a discussion as to why you didn't even know where to start for this one. Probably shouldn't be at that point right now. All right, so this one, a little bit more complicated. Most of it is in that you're having to ask multiple questions because I gave you three variables to work with. So this one's throwing in some logic and stuff like that. So what I would have expected everyone to be able to do is give me what's the return type, what's the name of the function, and show me you know how to take in 3 integer parameters. Okay, that's just piecing apart the question. Write a function, named midterm, takes 3 integer parameters, and returns a number. Okay, so get that header line on there. That should be a fairly easy toss-up at this point. And even if you miss that, that's something you should be able to do. So make sure you understand that. Once you get into the meat of this, the logic is always the last thing that kind of comes for beginning programmers. So even when you see it, it doesn't seem all that bad. You're just like, okay, well, it's just several if statements, not the end of the world. But still, you haven't done enough reps yet where your mind just immediately jumps to a solution. All right, so don't beat yourself up too bad there, but you certainly want to practice these types of things because really, if you remember from the first week of class, I mentioned that what makes programming hard is not the syntax. It's not C++ or Java or Python or whatever it is. It's that you've spent your whole life solving problems as a human being. And now you're having to break those steps down to something that you have to explain to this computer, right? If I handed everybody in this room 3 note cards with 3 numbers on it, every one of you would be able to hand me the card out of the 3 that represented the smallest number, right? You wouldn't even think about it. It's like, okay, well, here you go. Smallest number. The challenge here is I asked you to say, how did you do that? Make sense? And you're not used to doing that. So keep reminding yourself of it, that that's the fight you're in, not learning C++. C++ doesn't matter. It's a stupid language, right? You'll complain a little bit when we talk about pointers here pretty soon because memory addresses are scary, but that's more of an intimidation factor, right? So kind of like stepping in the ring with Mike Tyson. It doesn't matter if you're going to win or lose. It's not comfortable. It's not going to be comfortable. All right. So try to keep that context in your head when you're trying to evaluate why you did poorly on the exam or something like that. Ask yourselves, why did I do poorly? Is it that things just haven't clicked yet? Is it that I haven't spent enough time on my homework? Something I mentioned to a student today is you need to really make sure you're typing out your answers and you're debugging it. I know you write 8 lines of code and you have 30 errors. I get it, right? And it's usually from some semicolon or a missing comma or something like that. But you really need to do those reps of, typing stuff, trying it, seeing it doesn't work, then taking let's say an educated guess. Don't just randomly change stuff until it works. Just you go through every single permutation of 700 characters on your screen until you finally get something that works. But you really need that muscle memory of, fixing the missing semicolon or fixing the semicolon that you keep forgetting to put there over and over again until that becomes very second nature to you. I mean, you even see some of the evidence in it from something that happened a couple of minutes ago for me. Every single time you see me write an if statement or a loop, I started off right away by having an opening curly brace and a closing curly brace, and I build my sandwich in between. That's something that must have been something I was error prone to when I was first starting to program years and years and years and years ago, right? And it's something that many of you have already seen. That's a struggle, is making sure you have the right number of curly braces, right? When in doubt, add curly braces. It seems to be the approach for beginning programmers. But taking little steps like that, coming up with little kind of defensive tricks that will make you less error prone, is something that really you need to put the reps in to being able to do. Okay. But this might be a question that some people would have struggled on, just because it's coding and it's making you think and you're under the pressure of time with the test and all those things. So you'll get better at it over time. Similar to this one, it wasn't hard logic, but I asked you to kind of put two or three little problem solving approaches together into a single step. This one maybe would have been a little bit more difficult, but everybody should have been able to come up with a method header. What's the return type? What's the name of the function? What are the parameters it takes? Maybe then have the loop that goes through everything, but maybe not quite sure how do I ask the question about what's evenly divisible by 5, that kind of thing. Yeah, so that kind of approach. This one should have been a layup. Everybody should have been able to get this one. Variable scope as well. Boolean expression as well. So really that's 10, 20, 30. Let's say 35, 45, 55, 65. I would say that realistically, everybody in here should have been able to get at least a 70 in the exam based on the difficulty of the questions. I realize not everybody's going to be in that thing, but when you look at it now, even if I give you zeros on the programming questions, a 70 was attainable based on what was asked and what I told you was going to be on the exam. Also keeping in mind, this is the first time you've had, for most of you, this is your first semester taking exams in college and first time taking a Littman exam. All my exams look like this, by the way, every one of them. So even in grad school, I always ask 10 questions. I don't want to grade more than 10 questions. So, all right. All right. So before I go on to some more stuff, anybody have any questions about the exam? And like I said, I might get them graded tonight, but I have my 6 a.m. coffee hour set up to grade tomorrow morning. So if you want to come and bribe me, I'll probably be at N7 Coffee Shop when they open in Grafton, grading away. So if you really did poorly, I like bacon. Like
I think I do know my binary, but a little bit of
Yeah. Well, once you see what you did and things like that, then you'll be able to back up and go and retrace your steps and maybe try to do the exam a second time and see if you do better the second time. Ultimately, remember that you can fix any grade you got on this with doing better on the final. If you got a 5% on this test, you can turn it into 100. Okay.
Like
any number.
I know.
As long as you do better on the final, I'll replace whatever you got on this with that grade.
It's like 70% of our grade, so
right.
The grade changed drastically.
Yeah. If you had a 5% in your midterm and you came into the final exam and got a 90, all of a sudden, instead of having a 5% and a 90, you have two 90s. Your grade will change drastically. All right. So at this point, there is no reason why everybody in this room can't still get an A in the class. All right. And the thing is, I realize it's stressful having such a high percentage of your grade being based on an exam. First of all, understand that I'm actually a fairly friendly grader when it ultimately comes down to it. But also think back to the very first week of class when I was trying to tell you this is like a sport. You're practicing for the big games. And I grade easier in the 200 class than I do in the 250 class, than I do in the 300 class, and so on and so forth, because I want you to be encouraged to keep moving forward, but you also need to be held accountable for the putting in the reps. If you're on a sports team and you're not showing up to practice and then you come to the game and you suck, well, the coach might say, hey, keep up the good work. I see you working really hard at practice and things like that. And, they can be encouraging, right? But if you don't show up to 2/3 of the practice, you're sitting there napping on the bleachers, right? Coach is not going to be really surprised that you're not playing well in the games. So your goal as a good student is to work really hard at practice, and that will start translating through in the games, I promise. Remember, I've been doing this for a long time, longer than most of you have been alive. And this class is every bit as good as most beginning programming classes that come through. You can all make it. Just got to hold yourself accountable for the time, because programming takes too much time. I mean, when you compare it to the amount of time you might spend on your other assignments and other classes, it might take more, because it's not just busy work, right? If you already know how to do this stuff, you might knock out an assignment in 5 minutes. But if you're a beginning programmer, you might be spending 3, 4, 5 hours on these homework assignments that you come to class and see solved in a minute and a half, right? And that's normal, right? Michael Jordan's going to hit 10 free throws in a row way before you will, if you're just learning how to hold a basketball. Got to work your way up to it. So I'm sorry, that's the nature of programming, but I promise you put in the reps, you'll make a good living. All right. So hopefully the trade-off is worth something. All right. So last time we were talking about strings, right? And we started talking about things like base addresses and stuff like that, which should have been a little intimidating, but now let's make it really intimidating. Yeah, that's what I've been waiting for. I've been pining for more intimidating. What's the site we use? Online GDB, right? All right. So we'll switch that over to C++. I'm just going to start a fresh thing here, since we're going to start talking about something called pointers. Pointers. And I actually referenced this last class when I drew this picture right here. We were talking about strings. We were saying how strings are collections of characters, right? But when we create our variable s, in this case, string s equals hello, what actually is getting stored inside of s is a memory address. The string gets put somewhere up here in memory, in contiguous memory. What does contiguous memory mean? Next to each other, memory in a row. And that's important for things like strings and arrays, because that's the way they work. We saw last time that if I want s at bucket 0, the math problem for that is base address plus 0 times the size of a char, If I want S at bucket 4, the math problem is base address plus 4 times size of char, which takes me to memory address 104, which is right here. So you only are able to access the individual elements of collections like strings, and we're going to start talking about arrays this week, if they are stored in contiguous memory. Now, the good news is the languages do that for you. But as computer scientists, we want to understand that that's how it's stored behind the hood, because sometimes that can help you or hurt you. And this might start getting into the area where you can maybe say C++ isn't my favorite language. Or if you're a hacker, C++ is my favorite language. And the reason being is when we look at some of these more modern languages like Java and C#, they have some, what I would usually call a quality of life features that make the programmer's life a little bit easier. And one of the things they do is they don't allow you to walk off the end of an array. So if you're in Java and you have a collection of 5 characters and you try to access character number 11, which is larger than 4, which would be the last legal bucket in that guy, Java is going to have a problem with that. Okay, because all of a sudden you are dancing around, because the math problem works. Base address plus 11 times whatever the size of your element is, that's going to be a real memory address. Except now you're going and looking around in memory that you don't own. That's some other program's memory in your computer, or it's memory that the operating system hasn't handed out yet. More importantly, it's memory that you didn't request. C++ and C, they let you go and play around in memory that doesn't belong to you. Which, if you are somebody who is trying to access memory that doesn't belong to you, that can be a benefit. So, for instance, any of you who use any sort of bots or cheat codes or things like that for some video games, and when there's a patch for the video game, you'll see that they release a new version of the bot or whatever, because it's looking for very specific memory locations where, and the defense that the game makers do is they change the location of things when they release an update, which then makes the bots break, which then means the people who write the bots need to change it so that it goes and finds the right things in the right place in memory. And they're using an older language like C and C++ that lets them do that. Okay? Where Java and C# would never let you do that, because realistically, there isn't a legitimate reason. There probably are very few legitimate reasons why you would want to go and access memory that doesn't belong to you. Maybe there's some weird example that you could say there that you could come up with. There's a legitimate reason, but not very many, right? So realistically speaking, we like to have fences built, and you can't jump the fence. Well, a language like C++ does let you jump the fence. It doesn't encourage you to jump the fence, but the problem is, as a beginning programmer, when you already are not overly skilled at debugging, when you jump the fence and it doesn't give you an error, you don't know that you've accidentally jumped the fence, right? You're down the street at a whole nother memory address. You're playing in somebody's backyard, and you have no idea that you're in the wrong place. Okay, but you keep getting the wrong answer in your program. You don't understand why it's not working. All your logic looks right to you, except this one place up here where instead of starting at the end of your string and working towards the beginning, you started at the end of your string and just kept going. So one little error in your loop might mean that you're trying to do logic to stuff that you don't own, and C++ will let you do that. You won't get the right answer, but it's not going to scream at you. Java would immediately give you something like an array index out of bounds error. Old school C and C++ was really fun, because if you did step into memory that wasn't owned by you, like memory that was owned by the operating system, you could actually crash your computer. So when I started writing C and C++ many moons ago, it would not be uncommon, if you're pretty error prone still, for you to be working on your homework and literally crash your computer and have to restart the computer because you've overwritten some memory that's owned by the operating system. Modern operating systems, though, have protections. So you're even though the C++ will let you walk into other memory, the program is running inside of a little pod where it doesn't really let you get into trouble from a perspective of crashing your computer. You might just have to stop the program and restart it and try to find out what the problem is. But you can imagine how frustrating that was when you're halfway through your homework, you forgot to save, you can crash your program, restart the computer. All right, so we want to talk about these things called pointers. So pointers are variable types that are capable of holding a memory address. Just like ints are variable types capable of holding whole signed numbers, and chars are variable types capable of holding actually whole unsigned numbers that are mapped to chars using ASCII. And floats are variable types capable of holding signed decimal numbers, yada, yada, yada. So we've already been exposed to several different variable types. We know how to hold integers. We haven't done that much with floats, but we get that you can hold 3.14 inside of a double or inside of a float. You can hold chars. We've worked with Booleans. Well, now we're introducing a new type called a pointer. And pointers are capable of holding a memory address. Don't overcomplicate it. That's what a pointer holds. It holds a memory address. So if I gave any of you a piece of paper that had my home address on it, do you think you have the mechanisms available on your phone with GPS or whatever, you can find your way to my house? Sure. That's a pointer. I'm not giving you my house. Houses are heavy, right? Instead, I'm saying, here is where you can find my house in the world. Here's where you can find this variable in computer's memory. Make sense? Now, pointers are not necessarily better or worse than normal values. Sometimes they're actually somewhat interchangeable. There are some, we're going to get into it, some reasons why you might use pointers or you might avoid using pointers. But in general, pointers, one of the features of a pointer is it allows us to work with large pieces of information using just an address. Okay. If I've hired you to paint my house, it's going to be a lot easier for me to give you the address where you can find my house so you can go paint it, rather than haul it into the school and say, where do you want me to drop this off? Houses don't work that way. They're too heavy. Make sense? So in a case like that, that's why you would always expect somebody to give you the address of their house rather than give you the house. Same thing's true in programming. All right, so let's see some examples of pointers. I'm going to go ahead and just run my hello world program here real quick, make sure it's working. So there's my error-free hello world program. All right, so now I'm going to say int a is equal to 5. And I'm going to see out a. So what's the output of this program going to be? 5. Now, 5, a is a variable, right? A is like a little bucket that we're putting a value into. But where does that value actually get stored? Somewhere in our computer memory, right? Now, we don't need to know as a programmer where the operating system decided to store that value. We just need to know that if I needed to get the value of a, I can just ask for it by saying, hey, tell me what a currently holds. But if I were interested I can see where in memory A is actually stored. Big hexadecimal number. So at least the value I gave you on the exam was shorter than that one. Okay, remember what I mentioned, I don't know, many classes ago about how computer memory addresses are far easier than human memory addresses, even though they intimidate us. The second you look at that, that looks scary, right? Okay, but all houses, all memory addresses in the computer are all on one big long street. We don't break it down into a street number, a house number, a street name, a city, a state, a zip, a country, yada, yada, yada. We don't do that in computers. We just say, hey, there's memory, this giant street. And any value you're going to store is going to be somewhere on a house in that street. And this is the number of that house. Imagine if we wrote that in decimal. Even a bigger footprint, right? Same value, right? Same value, but larger footprint. What if we wrote it in binary? Well, binary, this one, so this is what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12, each one is 4 bits. Each one of those hextets can be represented as 4 bits. That's 48 bits. So 48 zeros and ones is what it would take to rewrite that address in binary. Same number. Okay, so the purpose the reason we chose to use hexadecimal is because it's actually shorter. It's more compressed. It's a better way of expressing memory addresses without having a wall of zeros and ones in front of us. All right, now these are 48-bit memory addresses, even though most of our operating systems today are 64-bit operating systems. Why do you think that we're only using 48 bits for our memory addresses rather than 64 bits? So we're missing 16 bits, right? It's because, and I mentioned it a few minutes ago, that our modern operating systems run things in a protected way. So what happens is our modern operating systems, they reserve 2 to the 16th unique memory locations for operating system only stuff that your computer program can't accidentally wander into. So this operating system, whatever is on the back end of this guy, probably Linux or something, but whatever operating system you're running on a relatively modern laptop from the last 10 years, let's say, is running a 64-bit memory manager. That's something you'll talk about in the 350 operating systems class. Okay, but that doesn't mean all 64 bits are used for uniquely identifying where user programs live. You get 48 bits of that for your user program. So that means you can only have 2 to the 48th power unique locations in memory that users can put stuff in, unless you're running your program as the super user, an admin, administrator, or whatever on your computer. All right, that makes some sense. Unimportant for us that this is 48 bits or whatever. From our perspective, what we're thinking about in here right now is we're learning about storing memory addresses, and that's what this dude is. That's a memory address. Okay, but we haven't actually stored a memory address. All we've done here is we've proven to you that we can show the memory address. So there's really 2 syntaxes that we have to work with memory addresses. Pointer syntax. We have the ampersand. Actually, I'm going to not put an arrow there because we will use arrows when we talk about memory addresses at some point. So this gets us the address of a value. So for example, int a is equal to 5. Cout address A will display where the value of A is stored in memory. Make sense? Now our other syntax is the star syntax. asterisk. So I can create a variable of type int pointer. And I'll call this guy a pointer. I'm going to set that guy equal to the address of A. So I have two variables here. I have a variable A of type int, and I have a variable named a pointer of type int pointer, which means it's capable of holding the memory address of an int. Memory address of an int is 4 bytes big, 32 bits. That's the size of the plot of land. All right. So now when I print it out, the output's going to be very similar to what we saw before. Probably the memory address is actually a slightly different memory address because I ran it at other times. We re-asked the operating system for some available memory. If I run this multiple times in a row, we might see, yeah, we're seeing different addresses because it's asking the operating system for different addresses. But now I'm seeing that I'm storing the value 5 in a variable named A, but I'm also storing the address where that lives in another variable called a pointer. Now, we don't know why we might use that yet, but we know we can store it, right? So at this point, what we're getting out of today's class is we now have the ability to store memory addresses of variables, and we can look at them. We don't really know what we want to do with that yet, but those are things we can accomplish. And keep in mind, what I'm telling you right now, this thing with pointers, these are things that professional software engineers don't understand. Doesn't that seem ridiculous, though? We've really discussed it in about 10 minutes, right? And it doesn't seem that bad. But the second you start looking at memory addresses, you start flipping out. Okay, that's like Halloween, right? All right, so we'll leave it at that. No assignment for Thursday, but I probably will give you one over the weekend because we're going to be looking at arrays next class using these pointers. Okay, I will see everybody then.